Okay, our next procedure is to take these two vectors, use what we've worked with the determinants, and see if we can compute the cross product. All right, V cross W. This is the procedure. I'm just going to give this as a statement of fact. You take the determinant. Across the top, you put the I, J, K vectors. The second row is the first vector, those components. In this case, 3, 2, 1, vector V. The third row are the components of the second vector listed. So this is 1, 2, negative 1. All right? And you compute the determinant of that vector. That is the cross product. What you compute out of this should be a vector. Well, let's see what we get. If you expand, and this is why before we were always expanding across the top row, because the top row always consists of these unit vectors, these standard unit vectors. So when you eliminate the top row and the first column, you get 2, 1, 2, negative 1. Now, instead of putting the I in front, I know I'm going to create a vector. Instead of putting I times this determinant, I'm going to put the I in the back. So I'm going to write the determinant times I, which is this minor. And then J, remember the middle term is always negative. It's going to be a determinant times vector J. Eliminate the top row and the middle column. This is 3, 1, 1, negative 1. 3, 1, 1, negative 1. And then finally, vector K is multiplied by that 2 by 2 determinant, 3, 2, 1, 2. All right, so we see what happens here. Eliminate the top row, eliminate the first column, 2, 1, 2, negative 1. That's vector I. Negative because it's the second position. Eliminate, that's 3, 1, 1, negative 1 times vector J. And then K, that's 3, 2, 1, 2. That determinant times vector K. The rest of this is computation. So this is multiply minus multiply. It's negative 2 minus 2 vector I. Now be very careful. Minus parenthesis, negative 3 minus 1. Be very careful with the negative signs. And then plus, this is 6 minus 2 times vector K. And what do we get? Negative 2 minus 2 is negative 4I. This is negative 4, but it's negative 4. Is it clear this is positive 4? Be very careful. Negative 4, and that's negative, is positive 4. And then 6 minus 2 is 4. I got 4s all over the place. All right? And so that is the cross product of those two vectors. Now, what I'm going to show you next is not required, but it does illustrate something interesting. Suppose you take vector V, and you can choose either of these. I'm choosing V at random. Choose vector V, and you form the dot product with what we just found. Well, that's a vector, that's a vector. You can form the dot product. Remember, the dot product needs to be a scalar, a number. Well, that's the dot product, which is first component times first component, second component times second component, third component times third component. And so that's 3 times negative 4. Second component is 2. Second component is 4. 2 times 4. And then 1 times 4. And what do we get? We get negative 12 plus 8 plus 4 is equal to 0. That is not a coincidence. Recall from our study of the dot product, if the dot product of two vectors is 0, that means those two vectors are orthogonal. It is not a coincidence that when we form the cross product of these vectors, that the vector we end up with, this negative 4, 4, 4, is orthogonal to this first vector. That is the interpretation of, that's one of the interpretations of the cross product. The cross product is always orthogonal to both of the original vectors we started with. We could take vector W, find the dot product with this V cross W, and that would also work out to be 0. The cross product is orthogonal to both of these vectors. What we have is this. We have vector V in space. We have vector W in space. And what we will have found is a vector which is simultaneously perpendicular to both of them. Now, this vector has many other vectors that are perpendicular to it. And this red vector has many vectors that are perpendicular to it. But when you take both of them together, I want a vector that is perpendicular to both of them at the same time. Well, this is perpendicular to the red, but not the yellow. This is perpendicular to the yellow, but not the red. The one that's perpendicular to both is this one, right? This vector is perpendicular. Now, a person might argue, wait, this one down here is also perpendicular. Yes, there are two vectors that are possible. The one we found is the one that uses the right-hand rule. And the right-hand rule says this: vector V is listed first, vector W is listed second. If you use the right-hand rule, where you go vector V first, vector W second, then your thumb points in the direction of the vector you just found. If this is vector V and this is vector W, then when you form V cross W, you're finding this vector in this direction, which is simultaneously perpendicular to those. On the other hand, if we had gone back and found W cross V, then we would have been working this W first, V second. Then this would have been the rule, and then our thumb would be pointing the opposite direction. We would have been found this direction. So if you form V cross W, you get a vector that's perpendicular to both. If you form W cross V, you get a vector that's perpendicular to both. But V cross W and W cross V are opposite directions of each other. So one is one is the other times negative 1, scalar multiple. So that's the computation for the cross product, and you should be able to practice that now.